so far we have discussed the step growth polymerization, the uniqueness of the step growth polymerization, the basic criteria, condition and the mechanism. You will see that a versatile polymers can be synthesized in a different method. So, before that I just want to highlight the chain growth polymerization, and then I will come to the different chain growth polymerization. Okay. So, here as you see from the step growth polymerization, now it is very clear that in the, if you plot, this is the molecular weight of the polymer and this is the conversion of monomers. Okay. So, if my red is chain growth polymerization, you will get like this one. That graph I am not doing any scale, is just to qualitative, okay. But this is good enough to understand, and this one is like this one. Okay. So, later so here you will see that the blue one is the step growth polymerization and the red one is the chain growth polymerization, where the reactive species exist, and this is very highly reactive. It immediately reacts with monomers, and after reacting with monomer, it and again react with another monomer, and the reactive species basically at the end of the oligomer. Okay. So, the reaction is very rapid, and at the particular time of the polymerization, at a specific time you will see that molecular weight of the you are getting a quite high molecular weight of the polymer. Although as I told that both have advantage, disadvantage. The main disadvantage of the step growth and chain growth polymerization, okay, is that that you cannot really control the polymerization. So, if you have a specific length, or if I need a specific architecture, or you need a specific PDI of the polymer, it is very difficult to handle with this kind of polymerizations. So, in the ideal condition, okay, I will prefer to have polymerization where the molecular weight is linearly dependent on the conversion of the monomer. That means, if I feed a particular mole of the monomer, I should be able to know that how much molecular weight polymer I am getting. Okay. So, this is called the leaving polymerization, leaving or controlled polymerizations, where you will get the well defined polymer. So, eventually this we will discuss, okay, later how we can make the chain growth polymerization to leaving polymerization. Essentially, the leaving polymerizations either will be chain growth or step growth, but the polymerizations will be here the leaving control to get the well defined polymer with specific PDI or controlling the structure of the polymer backbone. Okay. So, let us understand what are the chain growth polymerization. So, here you will see that as I told that if you have a monomer here, okay, there are a lot of monomer, okay, and if I make this monomer needs not to be highly reactive, but I have to make it reactive by reacting with some initiator. In most of the cases it is a radical, okay, or maybe other cationic, anionic. Okay. So, this have to make a reactive site like reactive, okay, species. This may be radical, this may be, okay, cationic, this may be ionic, okay, or it may be metal catalyzed. Okay. But I have to make a highly reactive species, and then what it will do, it will react with monomer available, and then this one you will get see. So, this one like that. Okay. So, this will not stop to a to oligomer, monomer, dimer, trimer or hexamer. It will actually grow in a like that. Okay, like that. So, you will get the high molecular weight polymer by this chain growth polymerization. So, as I told that initiation, propagation and the termination is quite visible in this kind of polymerization, where at a particular time, okay, let us say like this time, okay, here you will get the chain, you will get the high molecular weight polymers along with some monomers left, okay, but the step growth, the scenario is different. So, the main point I am telling that there has to be active site, okay, and this active site you have to generate by different ways, okay, that we will discuss in the following classes, and very brief way, okay, because before going to the coordination catalytic polymerization, the metal catalytic polymerization, we should understand the other protocols, otherwise we cannot really make a difference or make we cannot understand the concept of the polymerization. So, here the addition polymerization is a basically in some book you will see that this is the a chain growth polymerization, okay. So, this is actually similar concept wise. So, you will see that there are several chain growth or addition growth polymerizations are possible, like free radical polymerizations we sometimes call the FRP, okay. Cationic polymerization we call CP, anionic polymerization called AP, okay. Then coordination catalyst polymerization, that is basically our aim in this course, and free radical polymerizations are recently developed to the controlled radical polymerizations, some we call CRP, controlled radical polymerization, okay. So, that I will try to give a very brief overview of the different addition polymerization. So, in as I told that in the chain growth polymerization, okay, that one like say like this is my ethylene monomer, okay, and now it is you can polymerize by the free radical polymerization that we call the FRP, okay. So, here we routinely use some initiator, okay, as example like this is your that benzo peroxide. So, what happens if we give some heat, okay, this undergoes the homolytic scission, okay. So, homolytic cleavage, and you will get the like that. So, you will get the highly reactive. So, this is basically the reactive species, okay. So, here you this is the reactive radical here. So, as I told that this in the free radical polymerization, a highly reactive species you have to make it highly the reactive species, radical species obviously, which has short lifetime, okay. In carbon based radicals. So, this is the scenario where the radicals, the unpaired electron, the free radical is housed in one of the p orbitals, okay. So, this one the free radicals now reacts with monomer, okay, and this is also another initiator we routinely use, that is called AIBN. Okay. So, this is, you know, that this is the AJA this is the AJA type of initiator. So, you see that what is the driving force, it is very easily we can make the corresponding radical. So, what happens here, you like that, okay, and you make the this one, okay, and nitrogen comes out, dinitrogen. So, this is the driving force. So, the radicals we routinely we use for initiate the polymerization in the free radical polymerization. So, I will just give some examples of the free radical polymerization, and I will try to give the basic properties or the unique criteria for this kind of polymerization. Okay. So, let us so now it is clear that what kind of what we prerequisite. So, prerequisite is that I have to initiate the monomer by a reactive radicals. So, radicals can be formed easily by the homolytic cleavage, like here, okay, in this case. So, two ways we can do, that is the homolytic. Here all these two examples are basically through by the homolytic cleavage, and other one we can do the transfer of single electron from ion or molecule, from ion or molecules. So, this one is called the single electron transfer. So, two ways, homolytic cleavage or electron transfer. Eventually, this one is basically redox reaction. So, if suppose one species will giving the electron to make the radical cationic and ionic. So, that also possible. So, these are the two ways we can make or we can generate the reactive species. Okay. Fine. So, let us take some examples, okay, like this kind of monomer, okay, we can do the radical polymerization if you use the radical initiator. Okay, you can make the polymers. Okay. Now, I will just show on examples, okay, where R is equal to, let us say, phenyl, where it is so this the polymer will be polystyrene, okay. So, and the monomer will be styrene. Then we will understand the what are the mechanism, what are the steps involved, and what is the advantage or disadvantage. So, what happens? So, you first is the initiation generation of the initiators. So, I am just writing in a simple way, okay. So, like a peroxo type of initiator. So, this is the initiation. So, you will get this radical. Now, this one will, I am sure if you have taken any polymerization course, you have studied this, but I just try to refresh your knowledge on this polymerization, so that it will be easier at later stage. Okay. So, here now what you are getting. So, this is basically the reacting with the monomer, okay, and you will get this, okay. Okay. So, you here see that this attack on this attack here, and then, okay. So, you have to this is a radical attack. Okay. So, you have to careful, this is a convention is like that. Okay. If there is a anion, then we do like this one. I am sure you know this one. Okay. So, it represent basically single electron attack. So, then you will see that it first attack here, because this is sterically favored, here phenyl group is there. So, attack at the less sterically position, and then it undergoes further, then it undergoes this rearrangement. And why? Because this is more stable, because it is conjugated with the phenyl group. So, now you will see that this is my reactive end. So, there this is my reactive end. Okay. So, now as it is reactive end, so this is now will react with another monomer. Okay. And similarly, it will react with at sequentially with other monomers, and eventually you will get the like this. Okay. And still you see that this is my monomer. Okay. This is my the polymers with still active end. Okay. So, here you will now this is the active end. So, this is the propagation step, this is the initiation step. Okay. Now, this one can undergo the termination, or can also possible the chain transfer. I will show very briefly, but here you have there we have to consider the other one important point, like for when this kind of radical species when react with the monomer, okay, CH to CHR. Okay, I am putting here this one. So, there is two possibilities. One, this can react here, or this can react here. So, the two possibilities I will show you what will be the difference in structure. So, this is my R, and this is okay. First I am writing the two possibilities, and then I will explain what is the difference. Okay. Fine. Now, you will see that formation of this one, how it is happening. This is happening by reacting with this one. Okay. So, if we consider this is head and this is tail side. So, this is basically head to tail attack. Now, another possibility is, if we consider this is head. So, that means this is head in this monomer. So, another possibility is that this can attack with this one, and eventually you will get this product. So, this is the product with head to head attack. Okay. But as I told, because this is less sterically favored. So, head to tail is the most favored way of the attack. So, in the radical in this kind of scenario, you will get mostly head to tail attack. Okay. Now, in very quickly, okay, I will tell you the termination. So, here you will see that I am not writing the whole polymers, I am just writing only the active active end of the polystyrene. Okay. So, here you see CH pH, if you recall the last slide. So, this is the CH2 CH pH. Okay. Now, this is the radical. So, this is a very active. So, we can imagine that there is another because there are a lot of this kind of active species, the polymers with active end are there. So, this one, then like this one. So, this one now can react, okay, and eventually what you will get? You will get so, basically you are getting, this is one termination. So, coupling of the two radical, and you will be getting a polymer with just double molecular weight. Okay. So, that is the one way of combinations. Okay. So, this is just a combination or coupling of the two radicals, and the other one is possible is the disproportionation. How it is possible? Very interesting. Okay. So, again I am writing the only active end, and there like this one. Okay. Now, what I will be doing here, I am just doing this so that it is easy to understand. So, I am writing this way. Okay. So, this is pH. Okay. Now, this is my radical here. This H is homolytic cleavage, and this H. Okay. And now, this you are getting H dot here, and this H dot is basically coupled with this radical. This is active end, and there is a formation of the double bond. So, you are getting here the double vinyl function like the polymer with the double bond end. So, here you are getting the double bond here, and here it is H is there. Okay. And in this case you are ended with, so both are dead polymers. So, this is also dead polymer, this is also dead polymers. So, I am just repeating again because there is a not clarity in the drawing. So, in this disproportionation reactions you will see there is a this is the my radical. So, what happens, this H, there is a homolytic cleavage here, this is the homolytic cleavage of this CH bond, and this one, this radical, this free electron reacts with the free electron available after the homolytic cleavage of the CH bond. So, H dot is free now, this H dot reacts with this end and forms the dead polymer end, and here you are getting the polymer, all the dead polymer, but with the one alkene bond. Okay. So, this way the terminations are possible, and also there is another possibility of the chain transfer. Okay. That is again I am writing with another end with a reactive end, and suppose if there is any species which can react with this activant, this X A may be monomer, this X may be solvent, okay, or any other impurities or reagents. So, what may happen? This can give the reactions like CH2, then CH CH pH and this X and this A dot. Now, this is called the chain transfer. Here this is also another possibility in the free radical polymerization. This is one of the disadvantage. So, here you will see this is my dead polymer, okay, but this one is reactive. Okay. So, this then again can initiate or you can tell reinitiate the polymerations. Okay. So, you will get then a quite broad molecular distribution in the polymerization. Okay. So, this as the summary. So, this free radical polymerations is very well known and widely used in the polymer synthesis, but problem is that you cannot really have a good control over on the polymer architecture and the molecular weight. So, in a conclusion that the step growth polymerization, you will see step growth polymerization, it is a quite slow process, okay, and it's a quite slow process, but effective to make the polymers very well developed, well studied and very useful polymers like nylon, other fibril type of polymers, PET, okay, and many of them. Now, chain growth polymerations, okay, there are several possibilities are there. One is the radical polymerations, okay, that may be free radical FRP, okay. There may be the controlled, that we will discuss in the next class. There may be the anionic polymerations, okay, that also we will discuss in the next class, but as the summary what I want to tell that in the chain growth polymerization you will see we can make the high molecular weight polymers by the chain growth polymerization protocol, where the different initiators are involved, where the reaction, the polymerization rate is quite high, and you can make it a very useful method for a versatile to get the versatile polymers. So, in the next class we will discuss about the controlled radical polymerations, where you have all the disadvantage associated with the free radical polymerations, where the control the main disadvantage of the making the polymerization of the free radical polymerization is the not having the control, that will be solved partially. And then we will discuss the anodic ring polymerization to make you see that more living in nature, so that the controlling and to get the well defined polymers will be quite useful according to our willness, okay, according to other properties we are aiming for, and obviously the application we are aiming for. So, thank you very much, and let us meet in the next class again.